Anyways, it's time to get started. Good afternoon, everybody. Welcome to exciting afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Now, the first thing I like to do is ask, did any of you happen to drive by a gas station and think about half the weight of gasoline is alkanes? You know what an alkane is. Or did you happen to look at a tank of propane for barbecue and think that's an alkane? Did you happen to look at a candle, think half the weight of a candle is an alkane? I hope you do, because when you're through listening to me or watching my videos, organic chemistry is all around you, and it won't hurt to think about it. And I'm not going to give up. I've got the whole summer to convince you to do that. All right, let's go through today's game plan. Today, I'll be lecturing, continuing with aromatic compounds. Then we'll have our lab, and you'll be done. Now, important things. Uh, Tomorrow, I'll be going through the alkyne problem set in lecture. Show up if you can, and that way you'll be able to ask questions if you want. You can still ask questions by email. Remember, my email address is kwhite@elgin.edu. And you can also come to my office hours tonight and Wednesday night from 6 until 7:15. And let's see, anything else? I'm looking over here. Uh, don't forget, today I put out an email. I think most of you got it in, but the lab that we did last week is due today, and the lab we'll do later today will be due on Wednesday. Labs are always due the next lab period. And they're easy 11 points, so make sure you hand them in or you're going to miss out on 11 points. And 11 points could be maybe the difference between an A and a B. You don't know. So hand in your labs. All right. Everybody see aromatic compounds on their screen? Thank you. All right. Last week, I started talking about aromatic compounds. I showed you that great book, Napoleon's Buttons, which means I'd forgotten to do it over the weekend. I'll probably download an e-version from my local library, the tablet I have, because like good friends, good books, I like to go and visit every once in a while again, and I will. But anyways, we're talking about aromatic compounds. And the aromatic compounds are called aromatic because they originally came or isolated from spices and herbs. Example would be vanilla. And they're found to have unusual chemical properties and they're very stable. With time, they don't decompose easily. And many have a ring C6H6. Actually, realistically, this should be C6H5, but C6H6 is called a benzene ring. Now, as soon as you say the word benzene, any organic chemist would know the following immediately. One, Kekula. And Kekula is one of the great organic chemists ever. And his, I think about the early 1800s, give or take 10 years. And what made him great? Well, he did a number of great things in organic chemistry. The first one is he was the one who really came up with the reasonable structure for benzene, which I'll show you in a little while. Now, as soon as you say Kekula and structure for benzene, any organic chemist who knows organic chemistry and not lying to you would say, oh, Kekula is snake dream. Snake dream? Yep. What does that mean? Well, later in life, when he was in his 60s or 70s, many decades after he came out with his discovery of the structure of benzene. Oh, I'm going to use a fancy word on you. It's called elucidate. And elucidate or elucidation means to figure out. My PhD advisor loved that word. Well, anyways, he elucidated the structure of benzene. And at a symposium he was talking at later in life, someone asked him, how did you come up with that idea? And he said, well, I went to bed one night and I had a dream. And in that dream, a snake was chasing its tail. And eventually it got its tail and bit on, was going in a circle. And that's how he came up with the idea of benzene. Now, that alone is a lifetime achievement, but he did a few other things, like he was the first chemist or person, I don't know if they called them chemists back then in 1800, but first scientist to recognize that carbon should always have four bonds. That's called the tetravalence of carbon. That also would be a lifetime achievement, which he made. And he didn't stop there. He was one of the first to recognize that carbon atoms are connected together by chemical bonds and they can form long chains, which you've seen in the alkanes already, and the alkenes and the alkynes. And like I said, he developed that benzene contained three conjugated double bonds. Now, conjugated, as you learned in the problem set and we talked about in alkenes, means alternating single, double bonds. That's conjugated. And before I show you the next slide, let's go to my whiteboard. Now, benzene has 6 carbons, 6 hydrogens. And cyclic. And the question is, how do you come up with a structure? And what Kekula did was say, one way of drawing it would be this way. A 6-membered ring, it's no longer cyclohexane, it's benzene. And it has 3 double bonds. Remember, 2 lines is a double bond. 1, 2, 3. And it's double, single, double, single, double, single. You have alternating double, single bonds. That's called conjugated. Now, Kekula, this is called a Kekula structure, also determined what's called resonance. If I move this electrons here, then these have to move here, and these have to move here. In a later slide, I'll show you, we use a double-headed arrow, running out of room, to show resonance. And here's the other structure, Kekula structure of benzene. And let me rewrite it without the arrows. And you're not really rotating the ring, you're moving the double bonds. And they exist at the same time with each other. Now, another way, which I think these are cool, but another way, and I'll explain why, to write benzene is with a circle in the center that shows the aromatic character of the benzene ring. This is okay on a test, but in class, I'm going to do it this way or this way because I just think it looks cool. And those are the Kekula structures. And these are the way you would draw benzene. Now, a long time ago, I found this on the internet. Everybody see the picture? Is that a cool beard or is that a cool beard? I have to keep mine very trimmed short because at times I go to chemical plants and there's a possibility I may have to put on a gas mask. And a beard like that, anybody who's ever worn a gas mask, know you're going to break the seal and you're dead. But back then, obviously, he didn't have to wear one. And notice they have the structure of benzene in the corner. And he lived from 1829. I was off by a number of years. But in the 1830s or 40s, I believe, was when he came up with his idea for benzene. And notice DDR, That's Deutsches Demokratische Republika, otherwise known as East Germany. Now, for a number of years, I used to tell students, if you ever see this for sale, let me know. If it's reasonable, I'd like to buy one or two. And turns out 2 years ago, one of my Chem 170 students emailed me and said, look what I found on eBay. And it was the stamp. And sure enough, they had two of them. Were they reasonably priced? Well, they're in my house now. So the answer is yes. But this is one of the great of all organic chemists, Kekula. Now, as I mentioned earlier, we have what's called resonance. Resonance won't be on a test, but I still like to give you a little background. And these are the two Kekula structures. Now, back then, I really should take it off. I put brackets, but I wanted to illustrate that these are not structures you can isolate. They exist both at the same time. The arrows here showing the electrons moving, going back and forth. And that's why you have a double-headed arrow, because that shows you resonance, not a chemical reaction. Now, I did it already, but let me just remind you that throughout the semester, I'll be doing the following. Click, think of it like a light switch, and will this be on a test? And I've shut the switch, no, click, it's in the off position. But still background information you should be familiar with. So next couple slides, click, switches in the off position. Now, a double bond has sigma and p orbitals, which is when the carbon atoms share electrons, that becomes a pi bond. Now, the p orbitals are conjugated in a double bond to overlap to form pi orbitals, which is your double bond or second bond of a double bond. And this creates a ring or cloud of electrons above and below the plane of the ring. And this is how you know that just like a double bond can't be rotated, a benzene ring is flat. And we'll learn later on that has important implications of molecules that have benzene rings in it, including the fibers used to make bulletproof vests. We'll get that way down the semester. Now, here's each carbon with its p orbital. And when they share, this one shares with this, but it could share here. And so it's sort of like, have you ever seen children play Ring Around the Rosie? Think about that whole line. It's from the Black Plague. But anyways, they're all holding hands. And that's the same thing with carbon in benzene. If you look at it from above, well, time to see that Dr. White never should be in art school. Oh, hold on, that's one of my worst. If you're looking at it, hope I didn't injure anybody's brain with that artwork. If you look at it from the top, what you'll see is essentially this. And that's why that's one of the forms of benzene. I don't like it. I like writing in double bonds, the Kekula structures. Now, switch is still off. Some entrance exams ask the following. Now, how do you know if something is aromatic? It's any cycloatomic, and you can have other atoms. I'll talk later about that in the semester. Some of that goes to make things like hemoglobin, but that's way down the semester. But any cycloatomic or cycloalkene, when it has a molecule with 2n+2 pi electrons, that equals the number of pi electrons that are conjugated. So benzene has 6, therefore n is 2, it's aromatic. Again, switch click is totally off for this slide, but it's good background information. I've been told one nursing exam, entrance exam, asked which of these are aromatic, and you needed this. I would never ask that on a test. There are better things I could ask. Now, This is a calculus structure. I have one. Let's do the other resonance form. This is the delocalized pi. I like this because this looks cooler to me. And either one of these are this way. Now, turns out benzene, which is a common name, has been used for this molecule for eons. And IUPAC, in their infinite wisdom, and they've done this on a number of molecules, say, we're not going to get these people to change and call something else. So the IUPAC name for this molecule and the common name is benzene. And that you should know switches on. And this is benzene. Now, come on a test, if I were to write, draw the structure of benzene, you could draw that one, or that one. If you draw this, I'll give you 0 points because that's cyclohexane. And this is totally different from benzene. It's like, is your ear the same as your nose? No. Well, cyclohexane and benzene are that different. You have to put in the lines for the double bond or use a circle, either way. And if I were to ask draw the structure of benzene, one way of doing it are my 3 double bonds, or you could use a circle. I don't, I just think this looks cooler. Now, as I said, nomenclature, remember nomenclature is a fancy word meaning how do you name something? And IUPAC is the official organization for creating and governing the rules for oral chemicals, but the majority, like 85% of the rules, are for organic molecules. And this is benzene. Benzene is a liquid at room temperature. It's also a very hazardous chemical. This hazard wasn't really found out until 1950s. And unfortunately, people were hurt by this chemical. This attacks your major organs. And I'll talk more about it after the next slide. So this is the structure of benzene. There are 2 other structures I could have written. The other resonance form or the delocalized pi. I like these 2 myself, but any one of these 3 on the test, if I ask, draw the structure of benzene, by the way, if you haven't figured out, click, switch is on now, this would be benzene. Now, when you put a methyl group on benzene, this molecule has been around for eons, and they don't call it methylbenzene. People have been calling it toluene for eons. How it got that name, I have no idea. Someday when I have nothing better to do, I'll look up the history of the name of toluene. The same thing, benzene. There are better things I have to do, but it would be interesting. And therefore, this is called toluene. And toluene is also a liquid at room temperature. Toluene is both the IUPAC and the common name for this molecule. Again, IUPAC said, we're not going to get those organic chemists to change, so we'll just call it toluene, and they did. Now, both toluene and benzene are liquid at room temperature and very stable molecules. So for many years, they were used as a solvent in paints, lacquered paints, till the 50s, early 60s when latex paint, I'll teach you later in the semester about latex paint, came out. And both toluene and benzene will destroy your major organs, and you can see I'm not a medical doctor, rots out your brain. Now, unfortunately, I had I don't know, it was my mother's second cousin or third cousin. And when I met him when I was very young, he was in his 60s, and he had been a painter all his life. And painters back then in the 40s, 30s, and 50s used paints that had benzene or toluene as a solvent, which meant he was inhaling those fumes. By the time I met him at a family get together, uh, he wasn't all there. Most of his brain was gone. He was a couple steps up, unfortunately, from a vegetable, but it was sad. And I learned firsthand back then the dangers of toluene and benzene. Now, another indication of the danger of toluene, which is similar to bad in terms of inhaling affecting your body, this won't be on test, is toluene used to be a major component in glues, like model airplane glue. And I've never met anybody, but I've seen stories, people who sniff glue to get a high. And what was causing that high? Toluene. And what did it do to their brain eventually? Well, bad things. Another one, and I don't know if you people are old enough to remember, they've changed the formulation. Before computers, when you have to type things out, there was a great product called liquid paper. You made a mistake, you had this liquid, you put it on the paper, it hardened up to white, you could type over it again. Well, it turned out liquid paper had toluene in it also, and people were sniffing that and getting high and having serious medical things. And they've changed that formulation. Now, next one switches off. When you put this, I won't ask you, but when you put a vinyl group, a double bond on a benzene ring, that also has a name. And its IUPAC common name is called styrene. Now, I'll teach you later on about polymers. Polymers, poly, many units, sort of like molecules that are like a long freight train, and they're important in our daily life. My water bottle is a polymer. So is the rubber tires. But styrene, if you put it together, you make polystyrene. How many of you have ever seen those white insulated foam cups or cheap foam coolers made up of polystyrene? And this is a molecule that's used to make those. Switches off on styrene. Now, when we talk about uh, nomenclature of benzene, you can use numbers, but most organic chemists don't, and I'll explain that in a second. And that second is now now. Special names are used instead of numbers when you have disubstituted, di meaning two, substitution, isomers. And for my test, I'll expect you to know these. That's ortho, meta, and para. Again, when you have disubstituted, we don't use numbers. We use ortho, meta, and para. By the way, anybody ever hear of Ortho Pharmaceuticals, the big drum company? I wonder where they got their name, Ortho. Surprise, this is where. And if we were in a classroom, you'd be patiently waiting while I do the following. Let's try that one again. And hopefully you see the three compounds A, B, and C. Now, each one has a benzene ring. Each one has an ethyl group and an propyl. So if I look at A, that would be ethyl and propyl. Bad habit of mine, these should all be lowercase, but when you're handwriting, I do that. Don't ask me why. Benzene. This one is also ethyl and propyl. Benzene. And the last one is also ethyl and propyl. Benzene. Oh, I just forgot an important announcement. And that is after lab today, for those who'd like to stick around, I will go through and teach you how to eliminate test anxiety free of charge. Well, actually, it's not free. You have to sign up and pay for my course. I will take it out of the video. If you can't make it today, those who are listening to the video later on, come to my office hours or make an appointment to see me, and I'll be more than happy to teach you. I just don't want it on the internet. Now, I apologize for the screen being so crowded. Usually I don't do this, but if we were on a whiteboard, doing the same thing. All right, when you have disubstituted, meaning two substituents on a benzene ring, we use these names. Ortho, 1,2 disubstituted. Meta, 1,3. Para, 1,4. Now, if I look at this, this is on carbon 1, this is on carbon 2. Therefore, this is ortho, ethyl and propylbenzene. 1,2 disubstituted is ortho. You look at B, 1, 2, 3. It doesn't matter which way you count from either alkyl group. This is 1,3 disubstituted. This is 1, 2. This is 1, 3. And what do we call 1, 3? Meta. So this would be meta, ethyl, and propylbenzene, not 1 ethyl, 3, and propyl. Organic chemists like me, and also on the test, chemists who grade test, me, use it. Now, this last one is 1, 2, 3, 4. And this is 1, 4 disubstituted. And if we look at this nice chart somebody put on the screen for us, 1, 4 is para. So this would be para, ethyl, and propylbenzene. And that's where ortho, meta, and para. Now, this is the only place in organic chemistry this is used. How that evolved, one day I tried looking for an hour. They made it look good enough, and I couldn't find it. But organic chemists use this, and I do, because I'm an organic chemist. So let's go through. Again, when you have 1, 2 disubstituted benzene ring, 2 alkyl groups or 2 substituents, we call that, using the special names, ortho, meta, or para. 1, 2 disubstituted is ortho. So this would be ortho, ethyl and propylbenzene. 1,3 disubstituted. This ethyl group is on 1, and you count in the direction to give the other one the lowest number, is on 3. We call 1,3 meta, meta-ethyl and propylbenzene. And finally, when you have 1,4, notice the ethyl is on 1, 2, 3, 4, the end propyl is on 4. We call that para. So that's para, ethyl, and propylbenzene. Do not use this for cyclohexane. Common mistake on test ones. People do that. Guess what? I mark it wrong. This is only for benzene and toluene. So let's try one. And why don't you try this one on your own? Then I'll do it. See, Dr. White likes to share the fun. I say fun enough times, you believe me. See how sneaky I am? And when you're done, give me a thumbs up. For those of you who have your webcam off, use your emoji buttons in Zoom. I should put up here. Once in a while, I'll use this. All right. Looks like everybody's done, so I better get to work. All right, what do we see? Remember, when you're looking at an organic molecule, look for what's different. It's not a carbon-carbon single bond or carbon or hydrogen atom, should get your attention like that. And we have double bonds in a ring, 6-membered ring. That's benzene, not cyclohexatriene. I've seen that on tests, and that's wrong. It's benzene. What do we have on there? Ethyl group and 3 carbons to the center carbon, isopropyl. And notice this is 1, 2, 3, 4 disubstituted. 1, 4. Oh, look, someone wrote up here, it's para. So that would be para ethyl isopropyl benzene. Now, let me show you something important. Now, if we look at this molecule, you say, oh, that's benzene with a methyl and an ethyl group on it. But as soon as you see benzene with an ethyl group, that's toluene. So the root name here is toluene, not methylbenzene. But toluene, the methyl group, is considered a substituent, even though it's in the name, and it's given number 1, 2, 3. So this is considered disubstituted benzene ring. Therefore, this is ethyl toluene, and 1,3 would be meta. Again, methyl group on a benzene ring is toluene. I hope I'm spelling it right. Sometimes I get the O and U wrong in toluene. I think I got it right this time. If not, let me know. Remember, Dr. White does not walk on water unless it's frozen. Even then, I try and stay off it. So if I ever make a mistake, correct me. So the root name, toluene, ethyl, but the methyl group on toluene is considered a substituent. So this is 1,3, and that's meta. And why don't you name that? And to help you out, and when you're done, give me a thumbs up. I see one person done already. If you're done early, please be patient. I try and give everybody time to finish. Oh, I think everybody's finished. Let's do it. What do you see here? Double bonds in a 6-member ring, benzene, but no, there's a methyl group. So that's toluene. Next, oh, I have 4 carbons, 3 to a center carbon, and that's a T-butyl or tert-butyl. In a day or two, I'm going to be a lazy organic chemist and call it what we normally do, T-butyl. You can do both. And tert is short for tertiary, meaning 3. And notice it's 1,2 disubstituted, so that would make it ortho. So that's ortho T-butyl toluene. Now, remember, ortho 1,2 disubstituted, meta 1,3 disubstituted benzene ring, and para 1,4 disubstituted benzene ring. Now, the following you don't have to write down. Everybody know what that is? Going once, going twice. It's aromatic. Remember para 1,4 disubstituted? You can all groan now. And if you happen to be near a firehouse, you can go in there and make them groan. All right. So we use the names ortho, meta, and para for disubstituted isomers or molecules of benzene. Now, I didn't talk about it earlier, but there are some other substituents that you should know. And it's not only in benzene, it can be on an alkane too, but I didn't talk about it. And the first one, when you have a chlorine atom on a benzene ring or anything else, it's called a chloro group. A bromine is called a bromo group. Iodine is called the iodo group, and fluorine is called the fluoro group. Now there's another one, NO2, and notice the bond is to the nitrogen. You don't have to know this, but it's like this. And so the bond is to the nitrogen with 2 oxygens on it, which we write this way. That's called the nitro group. Now, there we go. It's Subtle Monday. You should know chloro is Cl, bromo is Br, iodo is I, fluoro is F, NO2 is nitro, not NO3, NO2. Again, when there's on a substituent, you should know Cl is chloro, Br is bromine, I is iodo, F is fluoro, NO2 is nitro. Everybody who's copying the sound have a copy down. Don't forget, anything I show you, notice up here where it says Chapter 4, Aromatic Compounds. That means this is available as both a Word and a PDF file in D2L in the lecture section folder. All right, now there are two other groups, or one other. I won't ask you to know the name, but I will use it, is SO3H. And that's called the sulfonic group. And a derivative of sulfonic group on a benzene ring is a key molecule, actually the key molecule, in all your laundry detergents. Next time you do your laundry with laundry detergent, you're doing organic chemistry. I'll teach you that later in the semester. And alkyl groups are, as we've already seen, like the alkyl groups on the alkane or cycloalkane or alkene or alkyne, methyl, ethyl, N-propyl, isopropyl, N-butyl, T-butyl, or tert-butyl. So let's do a few examples. Now, when there's only one substituent on a benzene ring, just like you learned for cyclohexane, you don't use numbers. So what would this be? Oh, benzene ring. And this is a chlorine, that's a chloro. So this is called chlorobenzene. And similarly, it doesn't matter which carbon. This is a benzene ring. NO2 is nitro. This is nitrobenzene. Again, no number because there's only one substituent on the ring, the benzene ring. And why don't you try that one? And by the way, that's the most ugly looking 6-member ring. Hold on. That's better. And I'll let you write that down. Then I'll scroll up to the table. If we were in class, I'd have the table on the projector screen, computer projector screen. I can't do that here easily. I know what I have to do. Not that. That. And now you can see what BR is. And when you're done, give me a thumbs up. I see a number you are All right, looks like everybody's all done, so I better get to work. So what do we have here? We have a bromine on a benzene ring. So this would be bromobenzene, all lowercase, but I have that bad habit of every once in a while capitalizing a letter. And bad habits I sometimes don't change. This isn't too bad. Now, when you have two substituents, you use ortho, para, and meta, just like I showed you before. And notice here we have a benzene ring, an ethyl group, and an iodo group. So this would be ethyl, iodo, benzene. Say that 3 times quickly. And notice it's disubstituted, and it's 1, 4 disubstituted, 1, 4 is para. So that would be para ethyl iodobenzene. And why don't you try this one? What would be the IUPAC name of the following molecule? And I'll help you out since you haven't learned it. Here's a big help out because you just saw it. I don't expect you to know it immediately. And if you're done already, please be a little patient. I try and give everybody a chance to finish. All right, I think everybody's finished, so I better get to work. What do we have that's different? Double bonds in a 6-member ring. That's benzene. There are 2 groups on it, chloro, and this is N-propyl. So this would be chloro, N-propyl, benzene, and if I call this 1, it's 1,3 disubstituted, which makes it meta. So that'd be metachloro and propylbenzene. Say that 5 times quickly. No, don't. And with that, if I look at my clock, it's time for a 5-minute break. I'm going to go stretch. I'll see you back at 1:55. That's when the big hand is on the 11. For those of you with digital watches, 1:55. See you in 5. Love that. By the way, I think I mentioned it. This is back when I was in high school. I was into whistles. This is a taxi cab whistle used by doormen back then, downtown hotels. There was a shop that sold these, and I found it, and I bought one. All right, let's continue on with the nomenclature of aromatic compounds. Oh, let's do one more. And why don't you try this one? I don't think I did this before, but what would be the IUPAC name for the following molecule? And when you're done, I see one person already is. Give me a thumbs up or the thumbs up emoji, or the other emojis work just as well. You want to use the faces or the party horn, go right ahead. All right, I think everybody's done. Let me get to work. What do we have here? A benzene ring, but oh, look, it's got a methyl group. So that's toluene. I think I spelled it wrong earlier. I had the U in the wrong place. Now that I think about it, well, it's one of the few words in organic chemistry I've been known to spell wrong. Fluoro, I always spell wrong. And a bromine is a bromo group. Now, toluene is considered a disubstituted, so that's 1, 2, 3, 4. So this would be 1,4. Oh, look up here, it's still visible. That's para. So that's para-bromotoluene. I apologize for up here. And I got it right. And I spelled it wrong here. Did I tell you I was the first one down in spelling bee? I had it right on the slide. But anyways, so this would be para-bromotoluene. Now, when you have more than two things on a benzene ring, then you use numbers. And let me give you an example. Oh, let's make it a nice one. Now, this way, even though it looks like the bond is to oxygen, it's really to nitrogen. That's just the way we write it normally. There's another way, but that's how my software would write it. And if we look at that, what do we have? We have a benzene ring, but we have a methyl group. So that would be toluene. I'm going to try and spell it right. And then, oh, NO2 nitro, but not one, not two, but three. And di is two, and tri would be three nitro groups, trinitrotoluene. Where are they? When you have a multi-substituted toluene, the methyl group is 1, 2, 3, 4, 5, 6. And notice on 2, 4, and 6 are nitro groups. When you see tri, you need 3 numbers. So it's 2, 4, 6 trinitrotoluene. 2,4,6 trinitrotoluene. Did I tell you organic chemists are lazy? 2,4,6 trinitrotoluene. That's hurting my jaw. Why don't we just call it TNT? And 2,4,6 trinitrotoluene is the active ingredient in TNT, dynamite. And how many of you have heard of the Nobel Prizes? I think most of you have. And there's one for chemistry, there's one for peace, there's one for medicine, a whole bunch of them. And who started that? Alfred Nobel. And where did he get the money for the Nobel Prizes, like the Nobel Peace Prize? He and his brother found a way of making 2,4,6 trinitrotoluene, otherwise known as TNT, safe. Trinitrotoluene is a liquid at room temperature, very dangerous liquid. Certain shocks will cause it to explode because it's an explosive. And think about the late 1800s, early 1900s, when you were transporting things by wagon, pulled by a horse. You hit a bump, go like that, and you're dead. Well, what they found, and do not ever try this at home, was if you mix the TNT with clay and other things, and I don't know, I've never worked in that area, and trust me, I don't want to. It's still a dangerous area. But anyways, it would be stable, and they could mold it, wrap it. You've seen it in the movies. I've never seen one live, nor do I need to, but sticks of dynamite. And how do you set it off? You use a blasting cap in there that explodes, that causes the others to explode. Now, sad story, even when they figured it out, it was still dangerous to work with TNT. And one of his plants blew up and killed Alfred's brother. Now, who used his invention? Miners, yeah. Well, who was the biggest buyer of explosives from Alfred Nobel? The militaries of various governments in the world, because they used those for bombs and other things in wars. And he made a tremendous amount of money. And think about it, and there's nothing wrong with it, but think about where did the money that came to set up the Nobel Prizes? It came from selling explosives used in war. This is one of the, how should I say, interesting aspects of life. And I thought I'd show you that. Now, I'm going to let you have some fun. What would be the IUPAC name of that molecule? Remember, when there are more than 2 groups on a benzene ring, you use numbers. And I'll give you a hint, that has 3. All right, I think everybody's done. Let's take a look at this. What do we have? A benzene ring, but it has a methyl group on it. So that would be toluene. Let's see if I can spell it right again. I did. And it has not 1, but 2 chlorine groups. 2 is di. Tri is 3. Tetra is 4. I've never encountered that in my career, so I doubt you will either. So it's dichloro, toluene, and this is 1. Therefore, the 2 chlorines are on 2 and 3. Since di 2, you need two numbers. That'd be 2,3-dichlorotoluene. Now, the question for this would be, well, let's do another one. These are fun. I already did that, so let's do. Why don't you try this one? By the way, that's iodine, and that's called an iodo group. And that's a pretty molecule. Oops. Uh-oh. One of the bonds fell off. Now it's correct. And for those who are watching me on YouTube, thank you for making me a YouTube star. Not really, but I hope they're helpful. If you know friends at other schools who are taking organic this summer, they can watch it too. And when you're done, give me a thumbs up. All right, everybody's done. So what do we have here? Benzene ring. And I have an iodo group. And I have 1, 2, 3. So it's tri iodo, and it should be all lowercase, but I'm showing you the difference here. And this is 1, 2, 3, 4, 5, 6. So it's 1, 3, 5 triiodobenzene. Now, when it comes to skill, an organic chemist or those learning organic chemistry should have when it comes to nomenclature, names, there's 2 types of skills, 2 types of questions I can ask on a test. But anyways, one is, here's the structure, give the IUPAC name, and the other is, here's the name, draw the structure. And if I were to ask on a test, draw the structure for the following, or 4, and 3 points each. And the first one I have there is benzene. If you drew that, I'd give you 0 points. Don't forget to put in the bonds for benzene. You could have also drawn another resonance form this way, or you could have used what's called a delocalized this way. And any one of those would be correct. I'll let you try this one. Draw the structure for toluene. I spelled it right. I'm on a winning streak now. Look out. All right, I think everybody's done. Toluene, you should know that's a benzene ring. Don't forget the bonds with a methyl group. And you can put that methyl group on any carbon. Most you're going to put it on top. Now, let's have some fun. And the question is, draw the structure for meta-bromo-nitrotoluene. Now, how do you decode this? You always start from the right. Benzene ring. Oh, I know what that is. Don't forget the bonds inside or a circle, otherwise that's cyclohexane. Then I have a nitro group, NO2, and a bromo group, and meta means disubstituted, ortho, 1, 2, disubstituted, meta, 1, 3, disubstituted, and para, 1, 4, disubstituted. So I have a nitro group, and you can go either clockwise or counterclockwise. Most of you are going to go clockwise, so I will. 1, 2, 3. Meta is 1, 3 disubstituted. I have a bromine. Now you could have also written it this way. And this is also 1, 2, 3 meta bromonitrobenzene. And why don't you try this one? Draw the structure for para-tert-butyl iodobenzene. And one of the benefits of learning nomenclature is when you look at the label of something you want to buy or you have purchased, you can see the name and you'll know the structure. And hopefully all of you are enjoying organic chemistry. Remember, if you have any questions, always ask. Because in my lectures, in my world, there's no such thing as a dumb question. Also, if you're not comfortable asking questions in a lecture like this, always feel free to come to my office hours tonight and Wednesday night. If you're working then and need special help, let me know, because we got Zoom. I can set up something easily. I don't have to, and you don't have to drive to ECC campus. All right, I think everybody's done. How do we decode this? We start from the right and move left. Benzene ring. Iodo is iodine. Tert-butyl, 4 carbons, 3 to the center. Para is 1, 4. So this is 1, 2, 3. And I have my T-butyl group. And remember, there's 4 bonds to carbon. This is one way. There are many ways you could have. This would be another one. And all you've done is rotate the ring 180 degrees. And remember, molecules are not glued on paper. They exist in 3 dimensions and move all around in air, if they're in the air or if they're in a liquid. Not so much a solid. Oh, let's try one more. And why don't you try this one? Draw the structure 2,4-dinitrotoluene. And remember, when you're done, give me the thumbs up. And by the way, doesn't it feel good you can do this stuff? It's permitted to say no, but you really should say yes. All right, I think everybody's done. Is everybody done? All right, let's do it. How do you decode this? You start from the right, move left. Oh, I know what toluene is. Toluene is a benzene ring with a methyl group. Nitro is NO2. Now, this is one where the nitro groups on carbons 2 and 4. And this would be 2, 3, 4. So I have a nitro group there and a nitro group there. And that's how you would draw the structure of 2,4-dinitrotoluene. Toluene, benzene ring with a methyl group, nitro, 2 nitro groups. They're in carbons 2 and 4. Now you could have put the nitro group on this side. All you're doing is rotating it 180 degrees. And that's how you do nomenclature of most of the simpler aromatic compounds, the one I'll be asking you to learn how to do. Now, normally if we were face-to-face, we would have on Monday and Wednesday, because that's the summer, the days I've designated as lab days, I'd lecture for 50 minutes. We take a 10-minute break. Again, we're face-to-face. You go to the lab room, and I'd give about a 20-minute introduction, and you get to go in the lab. Well, you're not going to the lab. And also, coming up on July 5th, I'm going to lose that whole Monday, which means I'm going to lose some lecture time. So don't tell anybody, but I've been stealing from the lab time, because after one or more times on Monday and Wednesday, I'll lecture for 50 minutes. We'll take a 5-minute break, and then I'll have the lab, and you'll get out early. Shh, don't tell anybody. But in real life, that would happen face-to-face. So it's lab time. And today's lab, don't forget the lab you did last week is due today. But today's lab deals with alkenes, double bonds. And this was made available to you on the assignment area D2L. You don't need it now. And this is what you would be doing in the lab if we were face-to-face. All I've done is I've given you the data, but you still have to use the same mindset to answer questions, understand it. Now, all hydrocarbons are flammable. In our organic lab, in any organic lab, you should never light a Bunsen burner or a match or a cigarette lighter because they'll usually start a fire. And as if we were working in a lab, in order to be environmentally conscious neighbors to Lake Michigan and the surrounding area, we have special organic waste bottles, which are properly disposed of by a company ECC hires to do that. Now, the first part, as I mentioned, these labs I wrote myself, even if we were face to face, to give students an experience with organic chemicals, which most of you probably don't realize you probably aren't going to get in your life. Now, the first one is I'd ask you to smell some organic chemicals, and some of them are also alkanes. And here, what you would do with the liquid on a small piece of paper. By the way, Dr. Daly, who's the laboratory manager, and is also a part-time faculty or adjunct like myself, who teaches the 2-semester organic, is amazing in the lab. And he cut up, I used to have students rip their own paper towels once he got hired to do the labs. It was about 5-6 years ago. Before then, we had to do our own. He cut them all little squares, and you can put some of it in there, and then you smell it. Now, the proper way to smell something that's on a piece of paper, or if you had a bottle, is don't do this, because you can get knocked off your feet. You smell it like this. And that's how you should smell things. When I worked at one company, Axo Nobel, which when I worked for it was called Axo Chemie, we made very hazardous chemical called amines. I'll teach you about them later. And they had a real kick to them, like ammonia. And new hires, you'd get a couple of people standing behind them when somebody was going to do this, their boss, and say, hey, smell this. And person would go like this and knock them almost off their feet, which is why he has a couple people ready to catch them and teach you don't stick your nose in a bottle. Well, I had already worked with hazardous stuff before in grad school. So when I went and joined that, they played that and they said, here, smell this. And I went like this and they all started booing. I said, what do you mean boo? I know how to smell things properly, and you should too. Now, if you were in the lab, I took the liberty of writing down some things, and hexane, octane, octene, limonene, and naphthalene. Now, naphthalene is a solid, and I should tell you, naphthalene is the chemical they make mothballs out of. I don't know how many of you have ever smelled mothballs. My parents and grandparents had them in our house. My grandparents had them in some of the drawers where they kept wool. We had a special closet in our house for that. It smelled like mothballs, which is to say they're all over the bottom because moths, I guess, like to eat wool. All right, next one. And the one after. Now, number of the experiments you'll be doing in the lab, you would have been doing it face-to-faces before organic chemists or chemistry in general had modern electronic instrumentation to help identify chemicals. You've seen them in the CIS programs on TV, which are sort of, how should I say this, Hollywoodized. Is that a word? Hollywoodized? But sort of puffed up to more than they actually do, but they just, some of them are pretty close. Organic chemists especially use visual tests, things that change color, help identify things. And the following next two experiments are dealing with visual experiments or identification. And they help you tell, does the molecule have a double bond or not, which is an important thing to know when you're trying to understand what is the structure. Now, I have it written here, but let's talk about addition of halogen. In this case, we'll use bromate to double bonds. Now, the general reaction I taught you, any double bond plus a halogen you'll break the pi bond and each carbon gets a halogen. Now, for this test, we'll use bromine. Why? Because bromine is a red-brown color, depending on the concentration of the solution. Bromine itself is a liquid at room temperature. We usually have this diluted. Now, bromine itself is a very hazardous chemical. It will attack your skin and cause damage to your skin, so you have to be careful. Now, years ago, I used to let the students do this, but first, you break the pi bond, and each carbon gets a bromine. Now, most organic chemicals are colorless, looking like water, or slightly yellow. Very slightly. There are exceptions, but the ones we'll deal with, alkenes, are like that. Now, this dibromo is usually colorless. So the test is, think about it. If you're putting in something to a colorless solution that's red, reddish brown, if there are no double bonds, it will turn reddish brown. If there is a double bond, it will make this, which is colorless, and it'll stay colorless. Good news, through the miracle of YouTube. Everybody see testing unsaturation on your screen? Hold on. You see that, right? Thumbs up, people. All right, let me play you this video. Enjoy. By the way, there's no speaking to it. And that's the bromine solution. I guess there is speaking to it. And notice how it's turning a reddish brown color. Now to the alkene with the double bond, notice how quickly it's reacting with the bromine. Eventually, if you put too much in there, you'll use up all the double bonds, but they didn't. Notice if you have with a double bond, it stays clear. If there's no double bond, it won't react and it gets that reddish brown color. Now, today's lab, you would
questions. What I'm going to do today is I'm going to demonstrate the addition of a halogen.
That always happens to me. I forget the YouTube keeps on going to new ones. I got to turn that off one day. I'll remember. If we're in a lab, you take, and this one I actually do, and I'll explain why I conducted. I have some test tubes, just like you saw in the video. I'll put in some of the hydrocarbon, alkene or alkane, add some of the bromine solution, mix it. Now it says wait 5 minutes. Now we wait about a minute or two, and then dispose of it. Now, one of the things I should teach you now, even though you won't be doing this at home, let's assume the Sharpie is a test tube. When you're mixing in a lab, never ever mix a test tube this way. Why? You can get chemicals on your hand and yourself or someone else around you, like your instructor. What you do, there are two ways. One is, again, assume this is your test tube with the chemical in it. You hold it tightly and you go 1, 2, 3, 4, and that will mix it. Don't tickle it. That won't mix it. You really got to go like that. Now, there's another thing which we have in our lab that's way cool. It's called a vibro mixer. And it's this rubber disc on a motor that goes up and down. You can control how fast it vibrates. And what you do is you put on the rubber plate, you take the test tube, hold it firmly, push it down. It vibrates real quick and mix it. Only takes about 2, 3 seconds. And either way, you do that. Now, if you look on the screen, I have, if you took cyclohexane, if I did, you'd see when I add the bromate solution, it shows red-brown. 1-hexene, clear. Now, depending on what we have in stock in the stock room, sometimes it's 1 or 2 octane. That's why I don't have the number. So let's assume for this lab, we had 1 octane. And then limonene. And then to make it interesting, I have unknown A and unknown B. And let's assume the district attorney of Kane County came to us and said, we have to know, does unknown A and B have a double or not bond or not? Because that will help us convict a heinous criminal or a criminal of a heinous crime. I'll let you fill in what heinous crime. We can convict them if we find out what it is. So for unknown A, when you add the bromine, it stays clear. For unknown B, it goes reddish brown. And later on, the questions at the end of the lab, you'll need to use all this data. Now, there's another reaction which I did not teach in the lecture. And remember, that reminds me, I better say, anything we do in the lab will never be on test in the lecture. Anything on a lecture test, I talk about in the lectures. This makes lab more fun because you're not thinking, oh, I got to take big notes for the lecture exams, but you still have to hand in the labs. Now, another reaction is a double bond reacting with potassium permanganate, KMnO4. Now, this again, I have it up here, is colorless or slightly yellow. This in solution, this is acidic, there's a little acid to help make it react in water, is a purple color. Really good purple, if I could spell it correctly, purple color. Now, when you react the double bond with potassium permanganate, it breaks the double bond and puts a hydroxyl group on each carbon. Now, this is called an oxidation. And when something is oxidized, something else has to be reduced. And that's the potassium permanganate. And what you form from this is manganese dioxide. So if you get this reaction to occur, you'll get, this is called the diol. Diol, I'll teach you later, is for alcohols. I won't ask that on the test. And you get manganese dioxide. Now, manganese dioxide, the best way All right, can you hear me now? For some reason, I clicked on my microphone. The best way to describe it as a muddy brown color. Think of if you're in certain parts of the United States, you have some dirt, you throw some water on it, and it looks that muddy brown color. And if you react a chemical with manganese dioxide and you see that muddy brown color, that indicates you have a double bond. And you'd be doing this in the lab too. And let's go to and that's your potassium permanganate. And I don't know why this thing is coming on the, and if you mix it with, in this case, they have a double bond, you couldn't see it. And that's that muddy brown color you see. Let's go back, see it again. Everybody see it? And I guess for me, that looks like muddy brown. And if you see that in a test tube, guess what? You've got a double bond. So what you'll be doing is, and by the way, some people, they don't want their skin purple for a little while. Usually it rushes off very quickly, but it also can, because of the acid that's present in the solution. I have students when we're working with dangerous things wear rubber gloves, which we provide free of charge. Well, not free of charge. If you were taking a lab, you'd be paying a lab fee. And what you do is put a couple, 10 drops of the dilute KMNO4 solution in a test tube, add about 5 to 8 drops of your alkene or alkane to be tested, then mix it like I showed you earlier, wait a couple minutes, and I have 10 minutes, usually after 5, and when you're done, we have a special waste bottle for potassium permanganate waste. And as you saw on the YouTube, if you have a double bond, it turns muddy brown. And here, cyclohexane, no double bond, purple. Cyclohexene, this is one cyclooctane, turns double muddy brown. Now, limonene, which I showed you, had 2 double bonds, and then unknown A and B. And when you add potassium permanganate solution to unknown A, you get a muddy brown. When you add it to unknown B, you get a purple color. Now, at the end of this lab, you'll notice here's what you have to fill out and hand in, and this is due on Wednesday. I'll say that again. This is due Wednesday. All labs are due in the next lab period, just like I would do week to week on fall or spring. And our next lab will be this Wednesday. Now, question 1, I asked you to draw the structures of the chemicals you are using above. Then here's 2 and 3. And then to help out the Kane County DA, here's question number 4. And notice, use your experimental results. Now, that's the lab. Now, normally I'd say goodbye, gang gesund, but hold on 1 second. Let me make a couple announcements. Don't forget tomorrow, we will be doing the alkene-alkyne problem set in lecture. You should be doing that. For those who are watching this video, make sure you keep up because you're not going to learn organic chemistry and do well the day or two before a test. And today, after I say goodbye, I will be teaching those of you who want to stick around free of charge, will actually paid to be in my class, my method, how to eliminate test anxiety. It works real good. And you can use it in other classes too. So with that, I'm going to say, and we won't take a break. I'll just go in and do that. And then I'll let you, if you want to stick around, it'll take about 10 minutes, 15 at most, usually 10. And with that, I'll say, remember, Gang gesund is Yiddish for be healthy. So I'll say, if you don't want to stick around for the method, Gang gesund, be healthy, goodbye. And I stole that from Granny of Beverly Hillbillies.